Hi everyone, I'm Claudio Argentino and welcome back. In previous video we talked about the cold seeps and the biogeochemistry of methane in marine sediment, and I left you with some geochemical dataset of gases from cold seeps, and I left you with the exercise of identifying the source of this methane gas. So in this video we are interpreting the data, I give you the solution, and hopefully foster some further discussion. So the dataset included the isotopic and molecular geochemistry of gases. You had two different areas and two gas samples for each area. And I also gave you three gas plots that you can use to plot your data. So let's start with area A. If we plotted it in the methane isotope plot, we see that the 2 points are falling within the field of primary microbial gas, and specifically in this CR field, which is carbonate reduction field. In the molecular and isotopic plot, we see again that they plot in the primary microbial gas field. And also, if we look at the isotopic composition of carbon dioxide, we see that they nicely match with the other two field of composition as a microbial gas. So we can say that the gas has a microbial origin, very likely from carbonate reduction processes. If we look at the second area, area B, the sample fall within the field of thermogenic gas, but it can also overlap with secondary microbial, you see. So we really have to look also at the other plot. The molecular and isotopic plot is showing that these samples fall here, again, thermogenic and biodegradation field. So we really need also information from the geochemistry of carbon dioxide to figure out if it's thermogenic or secondary microbial from biodegradation, right? So if we look at this third plot, we can definitely exclude that it is biodegradation related, because our sample again fell in the thermogenic field. So I would say we have a thermogenic methane and thermogenic gas, and I would say that it can be oil associated, so it comes from a reservoir that is also hosting oil, because we can see here that it overlaps in this OA, oil associated field, here, and also here. I have a couple of case studies that we can have a look at very quickly. Akon Mosby mud volcano is located in the southwestern Barents Sea. Here, as I said, it's a mud volcano, very circular shape on plan view, 1 kilometer in diameter, pretty flat domed shape. And the gas seeping out of this mud volcano is actually primary microbial. You see many samples have been plotted in this molecular isotopic plot, and they are in the microbial and probably carbonate reduction related. So this can be an example of a microbial gas coming out at a cold seep in the Arctic. And this is how it looks like at the seafloor. We have microbial meth, tube worms. The sediment is pretty black in color because it's highly anoxic. The sulfate methane transition is very shallow, a few millimeters to centimeters beneath the seafloor. Again, another white microbial meth surrounded by tube worms. As you remember from the previous video, this is related to methane fluxes and their differential spatial distribution in this area. So high methane flux in the microbial mat and lower in the tube worm areas. For the second case studies, I picked the layer-Upet fault complex. So this area is located in the western Barents Sea, shallower depth. We are on the continental shelf, around 400 meters depth. We see from this video, we were collecting some gas bubbles here, some rock sample, and you see, as soon as we remove the rocks, gas escapes in the form of bubbles. So the rocks are kind of capping and making a seal for the gas. And there are also some patches of microbial mat. So the layer-Upet fault complex is an example of thermogenic dominated gas. But I also selected this case study because in most coal seepage area dominated by thermogenic gas, we always find that it's mixed with microbial gas. So in this plot here, we see that there is no definitive thermogenic origin for the gas. It's not fully thermogenic. It feels a bit off the compositional field in here. In this CO2 and methane isotopic plot, we see mostly thermogenic, yes, but it has a broad range of isotopic composition, right, for methane mostly. But in this molecular field, we see it's not very wet gas. It kind of overlaps with the dry microbial gas dominated by methane, and a few samples are typically thermogenic. So actually, we interpret this type of data as related to a mixing of thermogenic and microbial gas. And I said that it is very common to find this as mixture of gases. We see that in all coal seeps in the Barents Sea, where there's a thermogenic component. And in your opinion, why does it happen? Well, if we think about it, the thermogenic gas is generally, not always, but generally produced at greater depth in the sedimentary column, whereas the microbial gas has origin in the shallower sedimentary column where the microbes can perform their processes. So when the thermogenic gas leaks from the reservoir, it rises through the sedimentary column up. It also can entrain some microbial gas. So at the end, what you see in your coal seep at the seafloor is a mixture of these two sources. That explains why we have this complex composition.